Hello and welcome back to ZFC Set Theory. In the last two lectures, we went over unions and intersections, both the binary kind as well as the arbitrary kind. You might want to watch those first as a refresher. But today we're going to prove a bunch of useful identities with these guys, so let's have at it. Here's our first theorem. If you take the union of any set with the empty set, you just get the set. And why is that true? Well, if you remember what definition of union is, it's the set of things in A or B. So this is the set of X such that X is an element of A or X is an element of the empty set. Okay, that's this guy. Okay, but if you're in A or you're in the empty set, well, this part, X is in the empty set, that's always false. So if you have a statement or a false statement, we can just simplify this. This is just the set of X such that X is an element of A. And what is that? It's just A. So there you go. Next theorem, if you take the intersection of any set with the empty set, you just get the empty set, okay? And now why is that true? Well, if we simplify the intersection of A with the empty set, this is just the set of X such that X is in A and X is in the empty set, right? But now here's the thing, X is in the empty set, this is always false. So whatever this is, something and false simplifies to false, okay? So the set of X for which false is true is the empty set, because there's no X that could make that true. So that proves the theorem. The next two theorems I'm going to put right together because they're related. If you take the union of any set with itself, you just get the set. And if you take the intersection of the set with itself, same thing. The technical name for these two properties is idempotent, by the way. You don't have to remember the name, but it might be helpful for some of you. So let's prove these. If you do A union A, well, that's just the set of X such that X is an A or X is an A. But here's the thing, saying X is an A or X is an A, that simplifies. That's just the same as saying X is an A. So this is the set of X such that X is an A. And what is that? It's just A, of course. Okay, so A union A equals A. And now to prove this, it's the exact same logic. We can even copy paste it, but the only difference with this one is going to be that when you do the intersection of A and A, it's the set of X such that X is an element of A and X is an element of A, because intersection corresponds to and, okay? But again, saying X is an A and X is an A simplifies to just saying X is an A. So this is the set of X for which X is an A, which is just A, okay? So that proves both of them. Here are our next two theorems, which are called the commutative laws. The commutative just means you can switch the order and it stays the same. So let's prove these, okay? Well, here's the thing. A union B is just the set of X for which X is in A or X is in B. But B union A, what's that? That's just the set of X for which X is in B or X is in A. And you know what? These two statements right here, these are logically equivalent. So therefore, these two sets have to be equal. Okay, so that proves this. Hey, now what about this guy? Well, same exact logic. A intersect B is the same as the set of X for which X is in A and X is in B. Remember, the symbol means and. But B intersect A is the set of X for which X is in B and X is in A. Okay, and now these two propositions are logically equivalent because saying you're in A and in B is the same as saying you're in B and in A. So therefore, these two sets have to be the same. Because that proves both the theorems. Next up are the two associative laws. Associative just means you can move the parentheses like this and it doesn't change what it is. We'll prove the top one first. Okay, to prove two sets are equal, we have to prove that they have the same elements. Okay, well, suppose X is an element of this guy. Well, that's going to be true if and only if, okay, the B in this guy, remember, this is a set of things which are in A or in B union C. So this is the same as saying that X is in A or X is in B union C. And actually, I'm going to write the or with the logical symbol. Okay, that looks like a V. Okay. Well, this part here that says X is in A, B union C, but this is really saying X is in B or X is in C. So this whole thing is saying X is in A or parentheses, X is in B or X is in C. However, this proposition here saying X is in A or parentheses, X is in B or X is in C, that's the same as saying parentheses, X is in A or X is in B, close parentheses, or X is in C. If you don't believe me, you can make a truth table. But what's this the same as? Well, this part saying X is in A or X is in B, that part is the same as saying X is in A union B. So either X is in A union B or X is in C. But what's this the same as? Well, if you're in A union B or you're in C, then that means you're in the union of this guy and this guy. Okay, so we showed that you're an element of this set if you're an element of this set and vice versa. So therefore, by the axiom of extensionality, these two are equivalent. So that proves the first theorem. Notice the associativity of the set followed from the associativity of the logical operator or. To prove the second one, all we got to do is change all our ors to ands and unions to intersections. But other than that, the proof's exactly the same. So here's the proof that the intersections are associative. Well, if you're in A intersect this set, that means you're in the first set and in the second set. Okay, recall the wedge means and. If you're in B union C, that's the same as saying you're in B and you're in C. But now to say X is in A and X is in B and X is in C, well, then that means all three of these things has to be true. But by laws of logic, that's the same as saying this. You can change the parentheses with and. Okay, but now this part saying X is in A and X is in B is the same as saying X is in the intersection of A and B. And finally, saying X is in this set and X is in this set means that X has to be in the intersection of those two sets. So therefore, the law holds. As a remark, that means it's safe to write expressions like this and this. The order of operations here is not ambiguous because whether you put the parentheses here and do this first, or you put the parentheses here and do this first, either way, we've seen they're both equal by the associative law. These next two laws are called the distributive laws because they look kind of like this from arithmetic. Let's prove this one first. So to prove this, guys, show that these guys have the same elements. So what happens if X is an element of this guy? Well, saying that X is an element of this guy is the same as saying X is an element of A and X is an element of B union C. Okay, but what's this equivalent to? Well, the B union C part, that's the same as saying X is in B or X is in C. Here's where we got to use a little bit of logic. If you say that you're in A and you're either in B or you're in C, then that's the same logically as saying either you're in A and in B or you're in A and in C. So this is logically equivalent to saying either X is in A and X is in B, or X is in A and X is in C. Okay, if you don't believe me, you can make a truth table to verify that. But now what's this the same as? Well, this part right here is the same as saying X is in A intersect B. And then this part right here is the same as saying X is in A intersect C. Okay, so we're saying X is in this set or X is in this set. Well, saying you're in one set or you're in another set is the same as saying you're in the union. So that means X is in the union of these two sets. X is in our first set, union our second set. Okay, and so look, these two sets must be equal since they have the same elements. That proves part one, this guy. What about our second part? How do we prove this? I'm going to copy paste it just for reference. We want to show that this is true. How do we do it? Well, if X is in this set, what is that logically the same as? Well, if you're in A union this, that means X is in A or X is in this. If and only if X is in A or X is in this guy. Okay. But now this part right here is saying X is in B intersects C. That's the same as saying X is in B and X is in C. So we can simplify this. Okay, and now here's where we have to use a little bit of logic. Now, what is this the same as? Okay, I'll give you a hint. We want to show it's the same as something that looks like this, but with ors and ands instead of unions and intersections. We want to show that it's the same as this. X is in A or X is in B, and X is in A or X is in C. So how do we know that these two statements are equivalent? Okay, well, here's the thing. This X is an element of A part has to either be true or it has to be false. If this is true, then our whole or statement is true or whatever, which simplifies to true. And again, on down here, if both of their X is an element of A is true, then we have true or whatever, which just simplifies to true. And then here again, we have true or whatever, which simplifies to true. So our whole statement here says true and true, which is, of course, true. Okay, so both of our whole statements evaluate to true. All right, now what about if this is false? Well, if X is an element of A is false, then false or some other statement just simplifies to whatever the other statement is. So this whole statement becomes X is an element of B and X is an element of C. And what about this statement down here? Well, if both these guys are false, then this left part here, false or X is an element of B, this just simplifies to saying X is an element of B. And then this part, false or X is an element of C, just simplifies to saying X is an element of C. So this whole thing simplifies to X is an element of B and X is an element of C, which notice it's the same as this. So in either case, we see these guys have to be logically equivalent. So this bottom guy, okay, this is the same as saying that X is in, this part's the same as saying X is in A union B. And this part's the same as saying X is in A union C. Okay, and now you're saying you're in one set and you're in another set. And is the same as saying you're in the intersection of those two sets. So this is the same as saying X is in A union B, intersect A union C. And so, hey, what do you know? These two sets have the same elements. So by the axiom of extensionality, they must be equal. So that proves our two distributive laws.